All right, here we are. We're back. Okay, so now let's suppose, here we go. We want to determine the electric field in a certain region of space. All right, so this one's not going to be hard because this is nice two-dimensional. You have a small object. This would be more like a test question. Small object of a known charge and an instrument that measures the magnitude and direction of the force exerted on the object by the electric field. We actually have such instruments. All right, so the object has a charge of positive 10 microcoulombs, and the instrument indicates that the force exerted on it is 40 micronewtons due east. What are the magnitude and direction of the electric field? Okay, well, let's draw the picture. 10, 40. Okay, let's start off drawing the picture. So here's the problem. Now this is a Go tutorial, so I'm not going to fill it out too much. But anyway, so I've got this positive charge. It feels a force due east, and the force is equal to 40 micronewtons that direction, and it's a positive charge. Okay, which direction is the electric field going? Got that right. The E field is going that way, and we know that the E field is equal to the force divided by this Q naught, where Q naught is equal to 10 microcoulombs, positive. Okay, so now let's take a look. Oh, I get some tulips. Final chance to get some tulips. I mean to turn off my thing before we do our thing. So anyway, so now what are the magnitude and direction of the electric field? The object has a charge of, and it's 20 newtons due west. Okay, the force is 20. It's a negative charge, and it's due west. What is this? Ooh, I said that this one was due east. I hope that's right. I'm going to submit. At least we'll get that one right. Oh, yeah. So that one's correct. I didn't put in any of the forces. And electric field, what is it? Newtons per coulomb. So let's at least do that part. Okay. Now you all figured this one out. Let's draw it, and then we'll move on. Okay. Here it is. Got Q naught is negative microcoulombs, and it's feeling a force that's due west. Which way is that? It's feeling the force is going this way. Which way is that electric field going? Remember, the electric field is being produced by a bunch of positive charges over here, going out like this, or a bunch of negative charges over here attracting like this. It doesn't want to go there. It's being repelled by this one or attracted to these. Okay, so you figured out from there. All right, cool. Sorry, my phone is going nuts. So that's a fun problem. So let's look at problem 31. Electric fields. What is that? 160,000 newtons per coulomb, points due west. So what is the magnitude of the force that acts? Oh, shoot. How many? Here you got the. This isn't bad, because here we have the electric field, and we have the charge, and we know this guy. Remember this. If E is equal to F over Q, then QE is equal to the force. I think that's what we're after. And but what were they asking? Did they want the direction? What is the magnitude? No, so it's all positive. So remember that. Magnitude means positive. All right? And last but not least, and we'll finish this lecture up. A lot of stuff here because we had to do the syllabus. And then in 2 days, we'll do the next one. So this one's much shorter than the last one. It's still pretty long. I mean, okay, review the features. All right, this will be fun. 3-point charges of 1Q, positive 2Q, and negative 3Q. All right, which one of these, which corresponds to the correct location of the field lines? Okay. Oh. I was like, what's the difference between these two? Ah, they cross right here. So which one of these is the correct representation of what the field lines look like? There you go. All right. See, not bad. Not bad at all. I don't think, yeah, I didn't ask you a Gauss's law question type thing. So um, I'm going to show you real quick before we quit here. All right, so let's do a Gauss's law type problem. All right, last thing we're going to do. All right, so let's say I've got a charge here of -3 microcoulombs, and it's sitting right here. And I've got a charge here of positive 5 microcoulombs. And I've got a charge over here of -7 microcoulombs. All right, and I want to find the electric field at a distance out here, P. What's the electric field out here being caused by these guys? All right, what is the uniform electric field that's being caused? You know what I do? I take all of these guys and I shrink them down to a point right here. And I go, okay, well that's +5 -7, which is -2 -3, so it's -5. So I'm going to shrink all these guys down into one point right here. Now remember this is, or let's say it's a point up here, off over here, a certain distance r. Okay, so say this was the sphere thing that we're doing. So I've got a net charge Q equals -5 microcoulombs. Okay, Q is equal to -5 microcoulombs. So therefore, if I want to find the E field out here at this point P, using Gauss's law, then here's what I do. I take the magnetic flux, which is E times the area, is equal to that big Q divided by E naught, which is the permittivity of free space. Okay? And then that permittivity of free space, and so I just got to solve for E. I take E is equal to Q. I've already done the analysis of Q. See, that was Gauss's genius, was to take all the charges and shrink them down to a point, add them up, and then just use the sphere because of how electricity worked. Okay, and then do the symmetry of the electric. Mother Nature loves symmetry. Where A, and since it's a sphere, we take the surface area of a sphere, which is equal to 4 pi r squared. If I want to find the distance r out here, then the electric field is equal to 5 times 10 to the -3 or -6 coulombs divided by 8.85 times 10 to the -12 coulombs squared per Newton meter squared, okay, times 4 pi, let's say it's 0.05 meter, r is equal to 0.005 meters, 4 pi times 5.0 times 10 to the -3 squared. Okay? And then that's the way I'd find the electric field. All right, that's page 3. That's chapter 18. A lot of stuff. A lot of stuff. In a couple days, I'll do one more lecture to get us started on chapter 16. That should keep you off the streets the first week of